Welcome to a new class of organic chemistry. In this video class, we are going to discuss 6 points on pyridine. So let's see. First point, pyridine is a 6-membered heterocyclic ring containing nitrogen, the molecular formula of which is C5H5N. Point number 2, pyridine has a conjugated system consisting of 3 double bonds and 3 single bonds. Needless to say that the 3 double bonds and the 3 single bonds are arranged in an alternating fashion. Point number 3, pyridine is an aromatic compound. The reason pyridine is aromatic is because it fulfills the 4 conditions of aromaticity. Condition number 1, the molecule should be cyclic. In pyridine, the first carbon atom is attached to the 5th carbon atom. That means pyridine is a cyclic molecule. Condition number 2, the molecule should be planar. If you look at the structure of pyridine, each of the carbon atoms of pyridine is a doubly bonded carbon atom. For a double bond to appear between 2 carbon atoms, the 2 carbon atoms should undergo sp2 hybridization and there should be an unhybridized p orbital in each of the carbon atom such that they overlap and form the pi bond or the double bond. As there are 5 doubly bonded carbon atoms, that would only mean that there are 5 sp2 hybridized carbon atom. Now after a carbon atom undergoes sp2 hybridization, the groups that are attached to the carbon atom, they assume the farthest positions available in space, and that would lead to a trigonal planar geometry around the central sp2 hybridized carbon atom. Now each of the 5 carbon atom, which is an sp2 hybridized carbon atom, have this trigonal planar geometry. That would only mean that the carbon and the hydrogen that are attached to it are in one single plane. That means the molecule of pyridine is a planar molecule. Condition number 3, the molecule should be conjugated. As we can see, after every double bond, there appears a single bond. The molecule of pyridine is no doubt conjugated. Secondly, there is a possibility that the pi electron may get delocalized to the adjacent position. If it gets delocalized, that would mean that the molecule is aromatic. But does that delocalization takes place? For this, we have to apply Huckel's rule. Huckel rule is 4n plus 2 pi rule. You write 4n plus 2 is equal to 6 resonating electron. 1, 2, 3, 4, 5, 6. 6 resonating electrons of the pyridine. 4n plus 2 is equal to 6. Subtract 2 on both sides. That would lead to 4n is equal to 4. N is equal to 4 by 4, which is 1. 1 is not important. What is important is n is not a fraction but a whole number. If you get n as a whole number, that would mean that the molecule under consideration is compliant with Huckel's rule. That is, delocalization occurs in the molecule, and that is that the molecule is aromatic. That means pyridine here has been proved as aromatic. Point number 4, the true structure of pyridine, note the point, is not the Kekulé structures but the resonance hybrid structure of pyridine, which is a combination of 5 resonating structures of pyridine, of which structure number 1 and structure number 5, the Kekulé resonating forms, have a major contribution towards the resonance hybrid structure, while structure 2, 3 and 4, the ionic resonating forms, have a lesser contribution towards the resonance hybrid structure. That is to say that pyridine spends most of its time as Kekulé resonating structure, structure 1 and structure 5, while it spends lesser time as ionic resonating structure 2, 3 and 4. But why is it so? Why is it that pyridine spends less time as ionic resonating forms? If we introspect structure 2, 3 and 4, the ionic structure, we would notice that there is charge separation in these structures. Charge separation requires additional energy, and because it requires additional energy, that puts these three structures at a thermodynamically higher energy level, while the structures 1 and 5 are at thermodynamically lower energy level. As for pyridine, it would prefer to spend its time at thermodynamically lower energy level, and it is for this reason that structure number 1 and structure number 5, the Kekulé resonating forms, have a major contribution to the resonance hybrid structure of pyridine. Point number 5. Pyridine undergoes electrophilic aromatic substitution, but under vigorous conditions. There is no doubt in anyone's mind that pyridine is a benzenoid compound. Being a benzenoid compound, it is rich in electrons. But there is a problem. We have a nitrogen here which is electronegative. And this electronegative nitrogen pulls an electron pair from the adjacent positions, and this creates scarcity of electron, particularly at ortho and para positions. Now, if an electrophile is given an opportunity to attack the pyridine ring, it would not do so. Why? As it is not attracted by pyridine ring, owing to the positive charge on the pyridine ring. Therefore, an electrophile would not attack pyridine ring at normal conditions. However, at vigorous conditions, it would do so. In contrast, if the electrophile is given an opportunity to attack the benzene ring, it would do it instantly, because benzene is a rich source of electron. Point number 6. Pyridine undergoes nucleophilic aromatic substitution with ease. We already discussed that there is a scarcity of electron, particularly at the ortho and para positions of pyridine. This scarcity of electron is because of the electronegative nitrogen pulling the adjacent electron pair towards itself. If a nucleophile is provided with an opportunity to attack pyridine, it would definitely do so at the ortho and the para positions. In contrast, if the nucleophile, which is rich in electron, approaches benzene ring, then as it approaches, it would be repelled, because benzene itself is rich in electron. Let us now look at the synthesis of pyridine from acetylene and hydrogen cyanide. When a mixture of acetylene and hydrogen cyanide is passed through red hot tube, the relatively more exposed pi bond undergoes homolytic fission. That is, the bond breaks and each of the atoms in the molecule get one electron each. After passing through the red hot tube, that is, on cooling, the electron on each atom now forms a fresh covalent bond with atoms of adjacent molecule, resulting in the formation of pyridine. Synthesis number 2 Dehydrogenation of piperidine. Piperidine on treatment with concentrated H2SO4 at 300 degrees Celsius undergoes dehydrogenation. That is, an H plus is eliminated from each of the atoms of piperidine, resulting in the formation of pyridine. The concentrated H2SO4 here is the dehydrogenating agent or the oxidizing agent. Concentrated H2SO4 undergoes thermal decomposition to form sulfur trioxide and H2O. Further, sulfur trioxide undergoes thermal decomposition to form sulfur dioxide and nascent oxygen. It is this nascent oxygen that eliminates an H plus from each of the atoms of piperidine, resulting in the formation of pyridine. Thus, concentrated H2SO4 is an oxidizing agent or a dehydrogenating agent. Synthesis number 3, Hansch synthesis. Two molecules of beta keto ester. This is the ester, the alpha carbon, beta carbon, beta keto ester. Two molecules of beta keto ester, a molecule of aldehyde and a molecule of ammonia undergo condensation reaction in which they lose 6 atoms of hydrogen and 3 atoms of oxygen in the form of 3 molecules of water to form diester 1,4-dihydro symmetrically substituted pyridine. This is the ester group. To remove the ester group, one has to subject it to hydrolysis. If you subject it to acidic hydrolysis, the H plus portion of the water goes and attaches to C2H5O, resulting in the elimination of C2H5OH from both sides. The OH portion of the water now goes and combines to the carbonyl carbon on both sides to form dicarboxylic acid. To remove this dicarboxylic acid, one has to subject it to decarboxylation. But decarboxylation is shown by the salts of acid and not acid. So therefore, one has to first convert it into its salt. As this is an acid by itself, if you are treating it with base, you would get salt plus water. Therefore, we treat this acid with sodium hydroxide, and that gives us sodium salt of carboxylic acid on both sides. Now, you can heat it with soda lime, which is CaO plus NaOH. When you heat it with soda lime, the ONA portion from the NaOH, it goes and attaches to COONA of the moiety to form Na2CO3. The H of this NaOH goes and attaches to the benzene ring on both sides via electrophilic aromatic substitution reaction to form 1,4-dihydro symmetrically substituted pyridine. Now, to synthesize pyridine from 1,4-dihydropyridine, one needs to remove 2 hydrogen atom and a pair of electron. To remove 2 hydrogen atom, now to synthesize pyridine from 1,4-dihydropyridine, one needs to remove 2 hydrogen atom and a pair of electron. That is, one needs to use a dehydrogenating or an oxidizing agent for this purpose. A mild oxidizing agent is enough for this purpose, as one needs to remove only 2 hydrogen atom. A mild oxidizing agent which is resistant to acidic conditions, as we are already using acid in the reaction previously. FeCl3, a Lewis acid catalyst, is befitting for this purpose, It is a mild oxidizing agent, as well it is resistant to acidic condition. FeCl3, Fe, has two half-filled d orbitals. These two half-filled d orbitals can accept two hydrogen and a pair of electron. Therefore, we reflex this with FeCl3. When we do this, a hydride reacts with FeCl3, a hydride eliminates from here and it reacts with FeCl3 to form FeHCl3-. The Fe, the two empty d orbitals of Fe, accepts the pair of electron and one hydrogen. Now when this happens, this carbon gets a positive charge. The positively charged this carbon now attracts electron pair from adjacent position, and therefore this electron pair, this bond, it comes here. When that does happen, this carbon is at loss, therefore this carbon becomes positive. This positively charged carbon now attracts electron from the adjacent pair, from the adjacent position. This electron pair between nitrogen and hydrogen is attracted and an H plus is dissociated. So the electron pair now lies here and lies here, while the H plus has been eliminated, and that results in the formation of a symmetrically substituted pyridine. Therefore, hand synthesis is used for the synthesis of symmetrically substituted pyridine. The H plus that eliminates now combines with FeHCl3- to give back the Lewis acid catalyst FeCl3 and hydrogen. Synthesis number 4 from tetrahydrofurfuryl alcohol. Heating of tetrahydrofurfuryl alcohol with ammonia in the presence of the oxidant aluminum oxide yields pyridine. Mechanism. When tetrahydrofurfuryl alcohol is heated, enough energy is generated to break the carbon-oxygen bond. The oxygen takes away the pair of electron while the carbon loses it. This results in a negative and a positive charge over the oxygen and carbon respectively. The newly developed nucleophilic center is attacked by a neutral nucleophile of ammonia. And in this process, because nitrogen lost its pair to the carbon, it develops a positive charge. To restore neutrality, nitrogen now pulls the electron pair that it shares with one of the hydrogen atom. In this process, it successfully does so. Meanwhile, the liberated H plus goes and attracts itself to the negative charge over the oxygen, resulting in the formation of OH here. Another hydrogen also gets attracted to the lone pair of electron on the oxygen, resulting in the formation of OH2 plus ion. And in this process, because the hydrogen lost its electron pair to the nitrogen develops a single negative charge. Another hydrogen, which is in near vicinity of the OH group on the right side of the molecule, now attracts itself to the lone pair of electron on the oxygen, resulting in the formation of another OH2 plus ion. And because it left its electron pair with the nitrogen develops a 2- charge over it. To restore the neutrality like it was before, the oxygen now pulls away the electron pair that it shares with the carbon on the left and the right side of the molecule, and that develops in a positive charge over the carbon atoms on the left and the right side. Now this right-sided positively charged carbon pulls the electron pair that is in the nearest vicinity of it, that is the electron pair that is shared between the carbon and the nitrogen. These have two implications. The first is that the CH2 now becomes a part of the ring, and second, that this C develops a positive charge. The C plus on the left side of the molecule attracts one of the electron pairs of the nitrogen, and this leads to development of a 6-membered ring. The positive charge that is on this carbon now tries to attract the electron pair on the adjacent carbon atom, and in this process an H plus gets dissociated. This electron pair now gets attracted to this carbon, resulting in the formation of the first double bond. Similarly, the negative charge on the nitrogen now establishes itself as the pi bond between the nitrogen and the carbon. To account for the fourth valence of the carbon, carbon loses its hydride ion. A hydride ion plus an H plus gives an H2 molecule. This is how one of the H2 molecules get released. And this establishes the second double bond in the ring. The third double bond in this ring can be easily established by the action of the oxidant aluminum oxide. Aluminum oxide releases oxygen, which can easily remove two hydrogen, one without any pair and the other one with its pair, leading to the formation of the third double bond within the ring and the formation of pyridine. Now we will look into the basicity of pyridines. In this section, we will ask ourselves 4 questions and we look forward to answering those questions. Question number 1, what is the nature of pyridine? Question 2, why is pyridine basic in nature? Question number 3, why is pyridine more basic than pyrrole? Question number 4, why is pyridine less basic than trimethylamine? Question number 1, what is the nature of pyridine? Pyridine is basic in nature. This is proved by its reaction with acid to form a salt. Question number 2, why is pyridine basic in nature? A Lewis base is a substance or a compound that have a pair of electron, and this pair of electron is available for donation to a proton or to a Lewis acid. Pyridine is a Lewis base. The structure of pyridine consists of nitrogen atom which has got a pair of electron that it can donate to a proton or a Lewis acid, and that's why pyridine is a Lewis base. Question number 3, why is pyridine more basic than pyrrole? To know this, we first need to introspect the structures of pyridine and pyrrole, and secondly, we need to know the state of hybridization of the nitrogen atom for the pyridine ring and the pyrrole ring. Let us first look at the structures of pyridine and pyrrole. X-ray diffraction measurements show that pyridine and pyrrole are planar. That means all atoms of pyridine and pyrrole are in one single plane. This is only possible if all atoms undergo sp2 hybridization, because it is only the sp2 hybridization that permits a planar geometry. Therefore, all the atoms, including nitrogen, of the pyridine and the pyrrole are sp2 hybridized. Now let us look how sp2 hybridization takes place for nitrogen. For this, we write the atomic number of nitrogen, which is 7. This is the electronic configuration, and here is the orbital diagram for the electronic configuration: 1s2, 2s2, 2p3. Let us first look at sp2 hybridization of nitrogen in the pyridine ring. 1s and 2p orbitals mix and merge with each other to form 3 new sp2 hybrid orbitals. The pz orbital does not take part in hybridization and is written as such. Now, one of the sp2 hybrid orbitals contains the lone pair of electron. There are other two sp2 hybrid orbitals containing one electron each, and they go for a head-on overlap with the sp2 hybrid orbitals of these carbon atoms on either side to form the Nc sigma covalent bond. Sigma covalent bond. Now, of course, there is a pz orbital that remains unhybridized, and because it is unhybridized, it remains perpendicular to the plane of the molecule or to the plane of the overlapped sp2 hybrid orbitals. This pz orbital, which is unhybridized, is now free to have lateral overlap with unhybridized pz orbital of sp2 carbon atoms on either side, and that results in delocalization, aromaticity, and an aromatic sextet. That is, it is the electron in pz orbitals, they contribute to all the three of these. On the other hand, the lone pair of electron is in sp2 hybrid orbital. It does not go for lateral overlap with the p orbitals simply because it is in another plane. It is on the plane, it shares the same plane as that of the plane of the molecule. Therefore, it won't go for any kind of lateral overlap. Thus, the electrons in the sp2 hybrid orbitals on the nitrogen atom for pyridine are localized. They do not participate in any kind of delocalization. Now, let us look at the sp2 hybridization of the nitrogen atom in the pyrrole ring. Now, this is completely different from what we have seen in sp2 hybridization of nitrogen in pyridine ring. How this occurs is being explained here. Before hybridization takes place, the electron in the 2s orbital jumps to the pz orbital such that the pz orbital consists of the lone pair of electron. It is now that 1s and 2p orbitals mix and merge with each other to form 3 new sp2 hybrid orbital. Each of the sp2 hybrid orbital now consists of one electron, and they go for a head-on, two of them go for a head-on overlap with the sp2 hybrid orbital of carbon on either side to form the Nc sigma covalent bond. One of the sp2 hybrid orbital goes for a head-on overlap with the s orbital of hydrogen to form NH sigma covalent bond. Now there is a unhybridized pz orbital which consists of lone pair of electron. Because it has not taken part in any kind of hybridization, it lies perpendicular to the plane of the molecule. It is now free to have lateral overlap on other unhybridized pz orbital of carbon atoms on either side, and thus the lone pair of electron in the pz orbital of nitrogen in pyrrole contributes to delocalization, aromaticity, and aromatic sextet. Let us now revisit our question, why is pyridine more basic than pyrrole? The answer to this is, in pyridine, the lone pair of electron are in sp2 hybrid orbitals. Being in sp2 hybrid orbitals make it localized because they are not in the same plane as that of the pz orbitals, and thus they do not take part in any kind of delocalization. As they are localized, they do not participate in delocalization. They are more readily available for any proton or for any Lewis acid. On the other side, if we look at pyrrole, the lone pair of electron is in a pz orbital, which can go for lateral overlap with unhybridized pz orbital of carbon atoms on either side. This can result in the lone pair of electron being delocalized. And because it is delocalized here, it would be harder for a proton to accept a pair of electron or for a Lewis acid to accept a pair of electron. And this is the reason why pyridine is more basic than pyrrole. Now, a question can come in the mind of a student that why there are two different kinds of sp2 hybridization for nitrogen of pyridine and the nitrogen of pyrrole. In the case of pyridine, there is no jump of electron from 2s orbital to the pz orbital. But in the case of pyrrole, there is a jump of electron from the 2s orbital to the pz orbital, and it is only after that jump that hybridization takes place. This is because by not jumping to the pz orbital, it makes the pz orbital potent enough to participate in the formation of an aromatic sextet. Meanwhile, on the other side, for pyrrole, by jumping to the pz orbital, it makes the pz orbital potent enough to participate in the formation of aromatic sextet. That is, whether the electron would jump or not depends upon whether such a jump would be advantageous to the formation of aromaticity and therefore in the stability of the molecule. Question number 4. Why is pyridine less basic than trimethylamine? To know this, we would have to introspect the structure of trimethylamine. X-ray diffraction technique shows that the trimethylamine is having a tetrahedral structure. For a molecule to have a tetrahedral structure, all atoms of that molecule should undergo sp3 hybridization, because it is only the sp3 hybridization that would permit a tetrahedral geometry. Therefore, all atoms including nitrogen undergo sp3 hybridization in trimethylamine. Let us see how sp3 hybridization takes place in nitrogen. The atomic number of nitrogen 7, electronic configuration, the orbital picture of electronic configuration 1s2, 2p2, 2p3. Orbitals of the valence shell, that is the second shell, take part in hybridization, mixing and merging with each other to form 4 new sp3 hybrid orbital. Amongst the 4 sp3 hybrid orbital, one of the sp3 hybrid orbital has the lone pair of electron. There are other 3 sp3 hybrid orbitals. They contain 1 electron each. They go for a head-on overlap with sp3 hybrid orbital of each carbon atom, forming an Nc sigma bond. Again, note the fact that the lone pair of electron is in sp3 hybrid orbital. sp3 has 75% p character and only 25% s character. That would mean that the sp3 hybrid orbitals have a larger lobe. A larger lobe or a longer lobe ensures that the electrons are much free to move. They are less associated with the nucleus of the nitrogen and are more available for a proton or for a Lewis acid. That makes the trimethylamine a very strong base. Contrarily, in pyridine, we see that the lone pair of electrons are in sp2 hybrid orbital. sp2 hybrid orbital has 33% S character and 66% P character. That means that the lobes are much shorter than it is for the sp3 hybrid orbital. Being much shorter, it restricts the movement of electron in a smaller space. More spherical shape ensures that the electrons are more associated with nitrogen, less free to move, and thus less readily available for any proton or for Lewis acid. Thus, without doubt, trimethylamine is more basic than pyridine. Now, let us look at the reactions of pyridine. Electrophilic aromatic substitution reaction. In this section, we'll ask ourselves three questions. Question number 1. Why is it that pyridine undergoes electrophilic aromatic substitution reaction only under vigorous conditions? Question number 2. At which position does electrophilic aromatic substitution reaction takes place for the pyridine ring? And question number 3. What are the examples of electrophilic aromatic substitution reaction in the pyridine ring? Question number 1. Why is it that pyridine undergoes electrophilic aromatic substitution reaction under vigorous conditions? There are two reasons for this. Reason number 1, presence of an electronegative nitrogen atom. Reason number 2, presence of a lone pair of electron on the nitrogen atom. Let us look at reason number 1, presence of electronegative nitrogen atom. Pyridine is an aromatic sextet consisting of 6 pi electron. It is this 6 pi electron that makes the pyridine ring susceptible to attack by an electrophile and thus undergo electrophilic aromatic substitution reaction. However, this reaction does not take place easily for pyridine. It takes place under vigorous conditions. But why is it so? To know the answer, we need to introspect the structure of pyridine. Pyridine has 5 carbon atoms and 1 electronegative nitrogen atom. It is this electronegative nitrogen atom that pulls the adjacently lying electron pair towards itself, and that makes an adjacently lying carbon atom positive in charge. What follows next is a cascade of electron pair transfer, which results in a positive charge at the ortho and the para positions. That is, in other words, the nitrogen atom pulls an electron pair from the pyridine ring, thus resulting in a great electron deficiency in pyridine ring. This makes the pyridine ring very unattractive to an electrophilic attack, and thus it is very difficult to initiate an electrophilic attack on the pyridine ring. Reason number 2, presence of an lone pair of electron on the nitrogen atom. If you ponder, you would wonder, why would the electrophile attack an electron pair that is delocalized? Rather, it is much easier for an electrophile to attack an electron pair that is localized on the sp2 hybrid orbital of the nitrogen atom. It attacks the localized pair of electron, resulting in the formation of a pyridinium cationic salt. The formation of pyridinium cationic salt is favored because The salt is stabilized by resonance. It is the cumulative effect of these two reasons that brings down the reactivity of the pyridine ring towards an electrophile. However, electrophilic substitution reaction is still possible in pyridine ring under vigorous conditions. Question number 2. At which of the position of the pyridine ring would the electrophile attack under vigorous conditions? That is, whether the electrophile would attack at position 3 or position 2 or position 4. To know the answer to this question, one has to compare the stability of the intermediate cations that are formed by attack of the electrophile at the third, at the second, and at the fourth position. Let us first look at the intermediate cation that is formed by the attack of an electrophile at the C3 position. The intermediate cation formed is a resonance hybrid structure of 3 contributing forms. To restore neutrality, an H plus is eliminated and the electron pair that is shared with H is taken in to form 3 substituted product. The same applies for attack at C2 and attack at C4. Structure A and structure B resulting from attack of an electrophile at the C2 and the C4 position respectively are nonsensical structures. That means structure A and structure B would never even form at the very first place. Why? Because these structures are high energy structures or they are very unstable structures. The reason of this is that the nitrogen atom in these structures are unstable. The nitrogen atom in these structures have only 1, 2, 3, 4, 5, 6 electrons in its valence shell. Here too, the nitrogen atom has 6 electrons in its valence shell. If you exclude these structures and look at other structures, be it from an attack at C3, C4 or C2 positions, other structures have a nitrogen atom in which the nitrogen atom has 8 electrons in its valence shell. Look at this: 1, 2, 3, 4, 5, 6, 7, 8. If you look at other structures, all other structures have 8 electrons in its valence shell. The nitrogen has 8 electrons in its valence shell, and thus the nitrogen has achieved the inert configuration of neon in these structures. That is not the case with structure A and structure B. It is for this reason that structure A and structure B have minimum contribution towards the resonance hybrid structure of the intermediate cation forms for attack at C2 and C4. Such is their contribution that their contribution is regarded as nil. That is to say that the resonance hybrid of the intermediate cation for attack at C2 is a resonance hybrid structure of these two, and the resonance hybrid structure for the intermediate cation by attack at C4 is a resonance hybrid structure of these two. On the other hand, the resonance hybrid structure is a combination of 3 resonating structures for attack at C3. Thus, the resonance hybrid structure of the intermediate cation at the C3 is more stable than at the C2 and the C4 position. Therefore, the attack at C3 position is preferable and it is the 3 substituted product that predominates. In case the third position is filled, attack would take place at the other available beta position relative to nitrogen atom, which is 5th position. Question number 3. What are the examples of electrophilic aromatic substitution reactions of pyridine? Example number 1. Nitration of pyridine. Pyridine, when it is treated with nitrating mixture, which is an equimolar proportion of potassium nitrate and H2SO4, under vigorous conditions undergoes nitration to form 3-nitropyridine. Mechanism: electrophilic aromatic substitution reaction has 3 steps. Step number 1 is the formation of electrophil. Potassium nitrate reacts with H2SO4 to form NO2+, which is also called as the nitronium ion. Nitronium ion is the electrophil in the reaction. In step number 2, it is this NO2+ that attacks at the most favorable position, which is position 3, and that attack leads to a resonance stabilized intermediate carbocation. In step number 3, an H+ from the third position is knocked out by OH-, which is a very strong base that has been produced in the step number 1. This same base deprotonates the H+ from third position. Simultaneously, the electron pair that the pyridine had shared with H+ is pulled in and to restore neutrality as well as to restore resonance, and yielding the product 3-nitropyridine. Now, usually in benzene, we are using HNO3 and H2SO4 as nitrating mixture, which yields the nitronium ion. Here we have used KNO3 in place of HNO3 to yield the same nitronium ion. But why? Why KNO3 in pyridine? KNO3 interacts with H2SO4 to yield a strong base, which is OH-. Had we used HNO3 in place of KNO3, then HNO3 would have interacted with H2SO4 to yield a mild base, which is HSO4-. In this reaction, we actually require a strong base like an OH-. The strong base, it can attract proton from third position with much greater intensity, and that would increase the electron density at the third position. NO2+ would now be attracted at a much faster rate. When there is a greater electron density at third position, NO2+ would be attracted much faster. So the reason why we have used KNO3 is to increase the rate of electrophilic aromatic substitution reaction. Even though we have used KNO3 to increase the rate of reaction, and even though the reactions of the conditions are vigorous, the yield of the 3-nitropyridine is very poor. It is only 8%. Example number 2. Sulfonation of pyridine. Pyridine on treatment with fuming H2SO4 in the presence of the catalyst mercuric sulfate and under heat undergoes sulfonation to yield pyridine 3-sulfonic acid. Mechanism: electrophilic aromatic substitution, which has 3 steps. Step number 1, formation of electrophil. Under fuming condition, one molecule of H2SO4 reacts with another molecule to produce sulfur trioxide. The molecule of sulfur trioxide exhibits resonance. It has 3 resonating structures. In all of these resonating structures, the negative atom is with each of the oxygen atom. Positive charge always rests on the sulfur atom. Therefore, it is a sulfur atom of the sulfur trioxide which acts as an electrophil. In step number 2, the sulfur atom of the sulfur trioxide attacks the most favorable position of the pyridine ring, which is position number 3, to produce an intermediate carbocation that has been stabilized by resonance. In step number 3, the HSO4- that was released in step number 1 acts as a base, a mild base, and knocks out a proton from position number 3. At the same time, the electron pair that the pyridine ring shared with that proton is pulled inside, and thus the neutrality as well as resonance of the pyridine ring is restored as it was in the beginning. It is good to remind ourselves that the oxygen of sulfur trioxide is still negative. It has a pair of electrons and thus acts as a Lewis base, ready to donate electron to any incoming acid. An acid is present here in this reaction. It was released in step number 1. It acts as an anhydrous acid because it can emit H plus from H2O. Therefore, it emits H plus. The H plus emitted H plus acts as a Lewis acid. It can accept a pair of electron and it accepts a pair of electron from SO3 to become SO3H, and thus the formation of pyridine 3-sulfonic acid. In the reaction of sulfonation of pyridine, we use the catalyst mercuric sulfate. Nitrogen is electronegative. It pulls an electron pair of the pyridine ring, thus causing great electron deficiency in the pyridine ring. Mercury of the mercuric sulfate is electropositive in nature. When it is in the near vicinity of pyridine, it pumps its electron to the pyridine ring. Thus, it somewhat counterbalances the electronegative effect of the nitrogen atom because it is electropositive. Therefore, the electron density of the pyridine ring is somewhat maintained when HgSO4 is in the near vicinity of pyridine. This increases the attraction of the electrophile SO3 plus towards the pyridine ring. That is, the presence of HgSO4 actually increases the rate of electrophilic aromatic substitution reaction, thus establishing the role of HgSO4 as a catalyst. Example number 3. Bromination of pyridine. Vapors of pyridine and bromine pass through activated charcoal to yield 3-bromopyridine. If the vapors of 3-bromopyridine persist over charcoal along with the vapors of bromine, then bromine would react with 3-bromopyridine to yield 3,5-dibromopyridine. Mechanism: electrophilic aromatic substitution. It has 3 steps. Step number 1. Formation of electrophile. Unlike UV rays, which can bring about homolytic fission of bromine, heat from charcoal brings heterolytic fission. That means one of the atoms in the molecule of bromine gets the pair of electron. The one that gets becomes negative. The one that loses the pair of electron is positive and is the electrophile. In step number 2, the electrophile Br positive attacks pyridine ring at the most favorable position, which is position number 3. For when it attacks at position number 3, it can get an intermediate carbocation having 3 resonating structures, and this is the intermediate carbocation. In step number 3, the Lewis base that is formed in step number 1 now knocks out a proton from 3rd position. Simultaneously, the pair of electrons that the pyridine shared with that proton is pulled in, thus restoring the neutrality as well as resonance of the pyridine ring and forming the product 3-bromopyridine. In the bromination of pyridine, the catalyst that is used is charcoal. Charcoal gives the necessary energy in the form of heat to break up these bonds. When these pi bonds are broken, the electron density at the 3rd position increases. This attracts the bromine instantaneously, and the bromine positive attacks the pyridine ring to give the substituted product. Therefore, charcoal increases the rate of electrophilic aromatic substitution reaction, thus reinforcing the role of charcoal as a catalyst. Pyridine does not undergo Friedel-Crafts alkylation or Friedel-Crafts acylation. This is because the Lewis acid catalyst, which is AlCl3 or FeCl3, does not wait for electron pair from alkyl halide in case of Friedel-Crafts alkylation or acyl halide in case of Friedel-Crafts acylation. Instead, the Lewis acid catalyst coordinates with the lone pair of electron on nitrogen to form pyridine aluminum salt if AlCl3 is involved, or pyridine iron salt if FeCl3 is involved. Question number 1. Why does pyridine undergo nucleophilic aromatic substitution reaction? Pyridine is an aromatic heterocyclic ring containing the electronegative atom of nitrogen. Nitrogen, because it is electronegative, pulls an adjacently lying electron pair towards itself, making the adjacently lying carbon atom positive in charge. What follows next is a cascade of electron pair transfer resulting in positive charge at ortho and para position. That is, in other words, the electronegative atom of nitrogen pulls an electron pair of pyridine towards itself, thus causing great electron scarcity in pyridine. This scarcity of electron in pyridine is denoted by positive charges, and it is this positive charge or region of electron scarcity which attracts a nucleophile towards itself, thus initiating nucleophilic aromatic substitution reaction. Question number 2. At which of the position would nucleophilic aromatic substitution reaction take place in pyridine ring? That is, whether the nucleophile would attack at position 2, at position 4 or at position 3. To know the answer to this question, one would have to compare the stability of the intermediate carbon anions that is formed by attack at C2, C4 and C3 position. Attack at C2 and attack at C4 involves intermediates A and intermediate B. In these structures, the negative charge is spread over the nitrogen atom. It also involves other two intermediates in which the negative charge is spread over the carbon atoms. On the other hand, attack at C3 involves only those intermediates in which the negative charge is spread only on carbon atoms. Structure A and structure B are very stable structures. The reason is that the negative charge is spread over nitrogen. Negative charge is very effectively absorbed over the shell of an electronegative nuclei like a nitrogen atom's nuclei. This gives them enhanced stability, and this makes their resonance hybrid very stable. Contrarily, attack at C3 involves those structures in which the negative charge is over the carbon atoms. Negative charge is less effectively absorbed over the shell of an electropositive atom like carbon atom in this case. This makes these structures relatively less stable compared to the stability of the intermediate B and A. And for this reason, the stability of the resonance hybrid in this case is less as compared to attack at C4 and attack at C2. This is the reason that attack at C2 and attack at C4 is preferred, and it is always that the C2 and the C4 product that predominates. Question number 3. What are the examples of nucleophilic aromatic substitution reactions of pyridine? Example number 1. Reaction with soda amide, otherwise called as Chichi-Babin reaction. Reaction: pyridine, when it is treated with soda amide at 100 degrees Celsius in the presence of dilute ammonia, yields 2-aminopyridine. Mechanism: nucleophilic aromatic substitution. 3 steps. Step number 1. Attack of the nucleophile. Nitrogen atom of the pyridine ring is electronegative. Being electronegative, it pulls an electron pair of the pyridine towards itself. This causes a great electron scarcity in pyridine ring. This electron scarcity is denoted by positive sign, and this positive sign is particularly high at ortho and para position. It is these positions that attract a nucleophile like an NH2- in this case towards the pyridine ring. However, attack has a preference at C2 position or the ortho position over the C4 position. Why so? There are 3 reasons for it. Reason number 1. Nitrogen, when it pulls electron, it pulls the adjacently lying electron pair, causing positive sign to appear at the ortho position first. Reason number 2. There are 2 ortho positions compared to only 1 para position. Reason number 3. The scarcity of electron or the positive sign, the intensity of positive sign is much higher at the ortho position than at the para position. This is because ortho position is in close proximity to the electronegative nitrogen. Owing to these 3 reasons, the NH2- has a preference to attack at the second position of the pyridine ring, and that yields to the formation of 2-aminopyridine carbonium ion. Step number 2. Elimination of the hydride ion. The 2-aminopyridine carbonium ion is stabilized by delocalization of electron at 3 positions, resulting in 3 resonating structures. All the 3 resonating structures are very stable. 2 of the resonating structures have electron density at the carbon atom, and one of the resonating structure has electron spread over the nitrogen atom. All the structures are stable, particularly the third resonating structure is very much stable and provides exceptional stability to the resonance hybrid structure of 2-aminopyridine carbonium ion. To retain neutrality, to restore its neutrality, the 2-aminopyridine carbonium ion tries to dispose of the hydride ion from its ring. However, the hydride ion is a very poor leaving group Sodium that was eliminated in step number 1 pulls the hydride ion towards itself, thus facilitating the 2-aminopyridine carbonium ion to lose the hydride ion and resulting in the formation of 2-aminopyridine. Step number 3. Formation of soda amide. The sodium from the formed sodium hydride is now attracted to the lone pair of electron of the nitrogen of the solvent molecule, that is dilute ammonia, that we have used in this reaction. As Sodium develops an attraction towards the lone pair of electron on nitrogen. It loses its attraction towards the shared pair of electron that it shares with hydrogen. Eventually, hydrogen is lost as hydride ion, and sodium accepts the pair of electron from nitrogen. But because the nitrogen has donated its pair of electron, it gets a positive sign. To restore neutrality, the nitrogen pulls the electron pair that it shares with one of the hydrogens, leading to elimination of H plus and formation of NaNH2, which is soda amide, that is the retainment of reactant. The H plus that is formed now combines with the H minus from the sodium hydride, leading to the evolution of hydrogen gas. Example number 2. Reaction with sodium hydroxide. Pyridine, when it is heated with sodium hydroxide at 300 degrees Celsius, yields 2-hydroxypyridine. Most of the molecule of the 2-hydroxypyridine is converted into its more stable keto form, which is here in this case 2-pyridone. Sodium hydroxide is a Lorentz-Brainsted base. That means that it dissociates spontaneously to yield OH minus. OH minus is the negatively charged nucleophile, and it can attack the pyridine ring, particularly at positions where the scarcity of electron is very high. That means at the ortho and the para positions. We have already seen in example number 1 that the OH minus nucleophile has a preference to attack at the second position over the fourth positions. We have seen the reasons in that example, and it attacks the second position to yield 2-hydroxypyridine. The 2-hydroxypyridine has an enol functional group, which is a OH group attached to carbon, which is attached to a nitrogen by double bond. And having an enol functional group means that it is an enol isomer. The enol isomer is comparatively less stable than the keto isomer. That means that most of these molecules would convert itself into its keto isomer at any temperature. 2-pyridone, the keto isomer, is more stable. The reason for this is that the carbon double bond O is a much stronger bond than the carbon O single bond. This means that more energy would be required to break the carbon double bond O than the carbon single bond O. More the energy required to break the bond, more the energy will be released in the formation of it. That would only mean that this molecule would have to release more of its energy to form a more stronger and a stable double bond O. And this is the reason that most of the enol tautomer converts itself into the keto isomer. The phenomena has already been discussed in an earlier video, which is titled the keto-enol tautomerism. Example number 3. Reaction with N-butyl lithium. Yet another example of nucleophilic aromatic substitution reaction is the reaction of pyridine with N-butyl lithium. Reaction. Pyridine reacts with N-butyl lithium at 100 degrees Celsius to yield 2N-butyl pyridine. Mechanism. The mechanism involved in the reaction is nucleophilic aromatic substitution reaction. Involves 2 steps. Step number 1 is attack of the nucleophile. This is the pyridine ring. It contains the electronegative nitrogen. Because the nitrogen is electronegative, it withdraws the electron pair, the nearest electron pair, towards itself, resulting in the positive charge at the second carbon atom. The positively charged carbon at the second position now attracts the neighboring electron pair towards itself, resulting in the development of positive charge at the fourth position. The positively charged carbon atom at the fourth position in the similar way attracts the adjoining electron pair towards itself, resulting in the development of positive charge again at the second position. As there is 2 times more probability of development of positive charge at the second position relative to the fourth position, and because of the reason that the intensity of positive charge would be higher at the second position owing to its closer vicinity to electronegative nitrogen, there is more probability that the nucleophile would attack this second position. The nucleophile in this case is N-butyl carbon anion. And how it is formed? It is formed because lithium actually donates its electron to the carbon atom attached to it. Lithium, on donating the electron, attains the inert configuration of helium, and that is the reason it donates the electron. And this is the reason why N-butyl carbon anion is formed. And when it is formed, it attacks the second position to form an intermediate where the nitrogen has 2 pairs of electrons. Step number 2. Elimination of hydride ion. The intermediate consists of the nitrogen atom, which has 2 pair of electron. One of the pair of electron is in the 2s2 orbital. The other pair of electron is in the 2px orbital. One of the electron of the lone pair of electrons of the 2px orbital is actually of the nitrogen. The other electron has been snatched from this carbon atom due to the electronegative pull of the nitrogen atom. In this situation, the nitrogen atom has 1 electron in excess relative to its proton. That is, in other words, the nitrogen with 2 lone pair of electron has 8 electrons and 7 proton. Because it has 1 electron in excess, the nitrogen atom is negative in charge. To restore neutrality and to become stable, the nitrogen would have to share this pair of electron with the carbon in covalent bonding like it was before. But in sharing, it faces a problem. The carbon atom here already has 8 electrons in its valence shell. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There are no empty orbital to accommodate this lone pair of electron. Therefore, now carbon, if it has to accommodate this lone pair of electron, would have to send away or would have to eliminate 2 electrons or a pair of electron. Therefore, the carbon eliminates the pair of electron that it shares with the hydrogen. Parallelly, hydrogen also has a role in abstraction of pair of electron. This is because on abstracting a pair of electron, the hydrogen can become inert helium configuration. That is, this would be thermodynamically stable. Therefore, the hydrogen abstracts the pair of electron, and the result is that this pair of electron is shared between the nitrogen and carbon, resulting in the formation of the product, which is 2N-butyl pyridine. The abstracted pair of electron by hydrogen is shared with lithium to form the lithium hydride. Let us now look at the other reactions of pyridine. Other reactions: oxidation, reduction, and reaction with methyl bromide. Number 1. Oxidation. Pyridine is not affected by mild oxidizing agents like chromic acid or nitric acid. However, when it is treated with a strong oxidizing agent like peracetic acid, It undergoes oxidation at the nitrogen atom to form pyridine N oxide. Well, to understand how this oxidation works out, we need to understand three things. Number one, what is peroxy acid and how peracetic acid is formed. Number two, how the peracetic acid decomposes itself to yield nascent oxygen. And number three, in what form the interaction takes place between nascent oxygen and the nitrogen of the pyridine ring to produce pyridine N oxide. Number one, what is peroxy acid? Peroxy acid is referred to as this group OOH. It is a very strong acid because the combined electronegativity of two oxygen atoms easily knocks out an H plus from the molecule. This group, the COOH, is referred to as the peroxy derivative of carboxylic acid, and the molecule as a whole is peroxy derivative of acetic acid or peracetic acid. How is it formed? Synthesis of peracetic acid. To form peracetic acid, you just need to treat acetic acid with hydrogen peroxide. The carbon double bond O of acetic acid is a highly polar one. This is because there is a difference in electronegativity of the two atoms involved in the bond. Oxygen is highly electronegative and therefore it pulls the electron pair that it shares with the carbon towards it, resulting in a negative charge over oxygen and a positive charge over the carbon. The positively charged carbon atom now acts as a Lewis acid and attracts a lone pair of electron from either of the oxygen of hydrogen peroxide. When it attracts, it restores its neutrality. But the oxygen which donates the lone pair, because it has lost its lone pair to carbon, becomes positively charged. To become neutral and to be stable, the oxygen now pulls the electron pair that it shares with the hydrogen, and that restores the neutrality in the oxygen atom. A problem persists on the other end of the molecule, where in the carbonyl oxygen, where an electron pair persists. This electron pair is shared with the carbonyl carbon, and this is shared because the oxygen wants to become neutral. However, when it is shared in covalent bond with this carbon, the carbon eliminates the electron pair that it shares with OH, along with OH. This is because the carbon can have a maximum of 8 electrons in the outermost shell, and this results in the formation of peracetic acid. The OH minus that is eliminated combines with H plus that was eliminated in the preceding step to form the H2O. Now, as the peracetic acid is formed, how does it decompose itself to produce nascent oxygen? The peracetic acid contains the carbonyl group. The carbon double bond O is a highly polar bond. This is because of the difference in electronegativity of the two atoms. The oxygen is highly electronegative, therefore it withdraws the electron pair that it shares with the carbon, thus becoming negative in charge. The carbon, because it has lost its bonding pair of electron, becomes positive in charge. The positively charged carbon atom now attracts the lone pair of electron of the neighboring oxygen towards itself, thus establishing a second covalent bond with this oxygen. However, because this oxygen lost its lone pair of electron to the carbon, the oxygen here becomes positive. To restore neutrality, this oxygen attracts and snatches the bonding pair of electron that it shared with this oxygen, and that results in the formation of an acetate ion. We can see how the double bond is established between the carbon and oxygen and how neutrality has been restored in this oxygen. But because this oxygen lost its bonding pair to this oxygen becomes positive. Now, this positively charged oxygen, as to become neutral, snatches away the electron pair that it shares with the hydrogen, resulting in the formation of nascent oxygen and elimination of H plus ion. The eliminated H plus ion combines with the carbonyl oxygen to produce acetic acid, and thus peracetic acid decomposes itself to produce nascent oxygen. Yes, a nascent oxygen is produced by the decomposition of peracetic acid. A nascent oxygen is a singular oxygen atom that has been produced by decomposition or any other chemical reaction. Its atomic number is 8. Atomic number 8 means that it has got 8 electrons, which is arranged as such in the orbitals. The molecular orbital picture clearly shows that it is in desperate need of 2 more electrons to complete its octet configuration. Let us now look at the situation of nitrogen atom in pyridine. The nitrogen atom in pyridine has already completed its octet and it is in no need of any kind of bond formation. The nitrogen atom here is sp2 hybridized. sp2 hybridized means that there are 3 sp2 hybrid orbitals in this nitrogen. One of the sp2 hybrid orbitals consists of the lone pair of electron. The other 2 sp2 hybrid orbitals are overlapping with the sp2 hybrid orbitals of carbon atoms on either side, forming the sigma covalent bond. Yes, there is an unhybridized p orbital in the nitrogen atom, and this is free to show lateral overlap with the unhybridized pz orbitals of carbon atoms on either side, thus forming the pi bond and thus forming a part of delocalization. In short, the nitrogen's octet is already complete. 1, 2, 3, 4, 5, 6, 7, 8. And therefore, it is in no need of any kind of covalent bond formation. The picture here, however, is different. The oxygen is in desperate need of 2 more electrons. This is the first reason that oxygen attacks the nitrogen atom. The second reason for the attack is that oxygen is more electronegative than nitrogen, and therefore oxygen attracts the electron pair that is available on the nitrogen. The third reason for the attack is that the lone pair of electron is localized on the sp2 hybrid orbital. The lone pair of electron on sp2 hybrid orbital does not take part in delocalization of the electron. It is localized, it is readily available for donation, and therefore the nitrogen donates the lone pair of electron to oxygen. Because the nitrogen has completely donated a pair of electron to oxygen, it develops a positive charge and the oxygen develops a negative charge, and the result, the product is pyridine N oxide. In a coordinate covalent bond, out of the 2 electrons that are donated, one of the electron is under the complete influence of the donor atom, the other electron is under the complete influence of the acceptor atom. That explains the unit charges that are developed on the atoms involved in the coordinate covalent bond. Number 2. Reduction of pyridine. Reduction is the addition of hydrogen atoms. A maximum of 1, 2, 3, 4, 5, 6 hydrogen atoms can be added to the molecule of pyridine. 5 of the hydrogen atoms would be added to carbon atom and 1 of the hydrogen atom would be added to the nitrogen atom. 6 hydrogen atoms means 3 molecules of hydrogen can be added to a molecule of pyridine. To commence the reaction, the hydrogen is pressurized through the finely divided nickel catalyst. Nickel has an atomic number of 28. Its electronic configuration from 1s2 to 3px to 3p6 is similar to that of argon. The number of electron and the arrangement of electron in the ensuing orbitals, which are 3d8 and 4s2, are unique and specific to nickel. For a much lucid understanding, we have drawn the orbital picture of the electronic configuration. As we can see that there are two half-filled empty orbitals in the 3d8 orbital, and it also has a 4s2 orbital which is fully filled. However, the 4s2 orbital is far from the nickel nucleus, and therefore it is under the least influence of nickel nucleus. That is, the electrons in the 4s2 orbital are free to move. They move freely, and they are under the least influence of the nucleus. Therefore, under the conditions of very high temperature and very high pressure, it is obvious that the electrons in the 4s2 orbital are knocked out. In this situation, the nickel would exist in its oxidized state, which is Ni2+. This is an electron deficient state of nickel, and it is this electron deficient nickel that attracts the electrons that are shared in a covalent bond between two hydrogen atoms towards it. This attraction of electron pair towards the nickel weakens the sigma covalent bond between the hydrogen atoms. Further weakening is bolstered by the very high temperature and very high pressure that are used in the reaction. The net effect of these two is that ultimately the hydrogen molecule dissociates into hydrogen atoms with one electron each. The hydrogen atoms with one electron each, they go for a covalent bond formation with the unpaired electron in the empty orbital, resulting in the formation of nickel hydrogen sigma covalent bond. In the next step, the pyridine, which is in its liquid state, is gently passed over the finely divided nickel catalyst. For the reason that nickel exists in its oxidized state, that is, it exists in its electron deficient state, the nickel would attract the pi bond that exists between each of the atoms in pyridine. Further, very high temperature and very high pressure would weaken the pi bond. The net effect of these two is breakage of the pi bond. With the result, each of the atoms of pyridine would get one electron each, and it is this one electron that is shared with the unpaired electrons in the 3d8 orbital of nickel that result in nitrogen nickel and carbon nickel single sigma covalent bond. Now, a point will come in the reaction process when the temperature would be lowered and when the pressure would be lowered. It is at this point that the nucleus and the electrons would have lesser energy. They would attract each other with lesser intensity. It is at this point that nickel would have very less influence on the electrons of its 3d8 orbital. Considering also the fact that nickel is very far away from the 3d8 orbital. The carbon, which has actually shared its electron with the electrons of the 3d8 orbital of nickel, also feels less attracted towards nickel now. Therefore, the carbon and the nitrogen would take away the pair of electron, resulting in negative charge over each of the atoms of pyridine. The hydrogen nucleus, which is in very close proximity to the pyridine ring, does not lose the opportunity and would leave its pair of electron with the 3d8 orbital of the nickel and attack each of the negatively charged atom in the pyridine ring, from below the plane of the molecule, that is from one side, to yield pyridine. Such type of addition from one side of the molecule is referred to as syn addition. Number 3. Reaction with methyl bromide. Pyridine reacts with methyl bromide to form N-methyl pyridinium bromide, which is a salt. In chemistry, a salt is an assembly of positively charged cation and negatively charged anion held to each other via electrostatic forces of attraction or ionic bond. A salt is electrically neutral because it contains equal number of cations and anions. Mechanism: bimolecular nucleophilic substitution reaction. The bond between the alkyl group and the bromide ion is a highly polar one. This is pertaining to the difference of electronegativity of both the atoms involved in the bond formation. The bromine atom is a highly electronegative one, and for this reason it draws the electron pair that it shares with the carbon towards itself. The electron cloud is now drifted towards bromine, and this results in a partial negative charge over the bromine atom and a partial positive charge over the carbon atom. As for pyridine, the lone pair of electron on the nitrogen of the pyridine ring is in its sp2 hybrid orbital. Because the lone pair of electron is in the sp2 hybrid orbital, it doesn't take part in delocalization of electron or in the aromaticity of the pyridine ring. This is because the sp2 hybrid orbital is in a plane that is perpendicular to the plane of pz unhybridized pz orbital. It is the unhybridized pz orbital of each of the atoms of pyridine that take part in delocalization or the aromaticity. In other words, what I mean to say is the lone pair of electron is isolated and readily available in the sp2 hybrid orbital of the nitrogen. It is this availability that endows nucleophilic property for the pyridine ring. The pyridine ring is a nucleophile, and to be specific, it is a neutral nucleophile. This compels the pyridine ring to attack the nucleophilic center, which is the positively charged carbon or the carbocation. However, when the attack takes place, it always takes place from the backside of the nucleophile, that is, in a position opposite to the position of the leaving group. What ensures is the formation of an intermediate where the groups are arranged around the positively charged carbon atom like the spokes of a wheel. An intermediate where carbon-bromine atom is partially broken and the nitrogen-carbon bond is partially formed. Succeeding to this, the carbon-bromine bond is completely broken and the nitrogen-carbon bond is completely formed. Because the nitrogen has donated its lone pair of electron completely to the carbon in a coordinate covalent bond, the nitrogen gets a positive charge and the result is the formation of an N-methyl pyridine cation. In the next step, the positively charged nitrogen attracts the negatively charged bromine towards itself and forms an ionic bond, resulting in the formation of N-methyl pyridinium bromide. Now, let us see the uses of pyridine. The first use of pyridine is as a solvent. Pyridine is a weakly basic polar aprotic solvent. Let us try to prove each of these points. Weakly basic. The lone pair of electron on the nitrogen atom of the pyridine ring lies in the sp2 hybrid orbital, which is in a different plane from that of from that of the plane in which the unhybridized pz orbital of each of the atoms of the pyridine lie. That is to say that the overlapping of these two orbitals is not possible. In other words, the electrons in the sp2 hybrid orbital are not or cannot take part in the delocalization or the aromaticity of the pyridine ring. In other words, the electrons in the sp2 hybrid orbital are available for donation, and that is what makes the pyridine ring basic. Not only, to be very specific, the pyridine ring is weakly basic. The reason for this again is that the electron lie in an orbital which has a greater proportion of s character. To be accurate, the sp2 hybrid orbital has 33.33% of s character. That would make the lobes broader and shorter, and that would make the electron come closer to the nucleus of nitrogen. A closer electron means that the electrons are more under the influence of the nucleus and are not readily available as was expected. That is, the pyridine is not as basic as we expect from it. It is weakly basic. Number 2, polar. Pyridine is a polar molecule. Pyridine has slightly polar bonds. This polarity is because of the difference of electronegativities of the atoms involved in the bond, which creates polarity, a slight polarity in each of the bonds of the pyridine ring, and overall the molecule of pyridine becomes slightly polar. The dipole moment here now becomes greater than 0. Third, pyridine is aprotic in nature. The term aprotic means capable of exhibiting hydrogen bonding. The pyridine ring has a nitrogen atom to which there is no hydrogen atom attached. Had there been an hydrogen atom, it would have exhibited hydrogen bonding. But because there is no hydrogen atom which is attached to the nitrogen atom, it could not show any kind of hydrogen bonding, and therefore the pyridine ring is aprotic. It's a solvent. Indisputably, pyridine is a solvent. It can stabilize and solvate the positive addendum of any reagent because it has got lone pair of electron to stabilize it and to solvate it. However, the counterpart negative addendum, it cannot solvate. That is, it can solvate cations but cannot solvate anions, and that would make the pyridine a mild solvent or a partial solvent. Let us now look into the utilization of pyridine as a solvent. Pyridine has often been used for its catalytic properties, and this catalytic properties is credited to the basicity that the pyridine ring has been endowed with. The basicity is due to the lone pair of electron that the nitrogen has. One of the examples in which the pyridine has been used for its catalytic purposes is the sulfonation of pyrrole and furan. Here, the lone pair of electron on the nitrogen atom of the pyridine ring attracts and forms a bond with the most vulnerable hydrogen atom of the ring, that is the hydrogen atom that neighbors the electronegative atom of nitrogen and oxygen. While it forms the bond with the nitrogen, on the other end, what results here is a development of negative charge on the adjacent carbon atom. It is at this negatively charged carbon atom that the electrophile attacks at the second step. In the third step, the attached sulfonyl group in the pyrrole and the furan ring abstracts the hydrogen back from the pyridine to form respective products, which is 2-pyrrole sulfonic acid and 2-furan sulfonic acid. What is notable here is the restoration of pyridine. The role of pyridine here is to speed up the reaction, take part in the reaction, but at the same time pyridine never forms a part of the product in this reaction. This places or positions pyridine as a catalyst. Yet another example where the pyridine ring has been used for its catalytic property is manifested in no even acyl condensation. In this reaction, the lone pair of electron on the nitrogen atom of the pyridine ring attracts and forms a bond with the hydrogen atom that is attached to the carboxyl group of the malonic acid. While it forms a bond with the hydrogen atom, it also speeds up the release of the carbon dioxide molecule, thus initiating the speedy formation of the product, which is alpha beta unsaturated acid. The byproduct formed in this reaction is OH minus. This OH minus now abstracts the hydrogen atom, which is attached to the nitrogen of the pyridine ring, forming H2O. On the other hand, it leads to the restoration of the pyridine ring. The reaction again reinforces the status of pyridine ring as a catalyst. Pyridine does not limit itself here. It also acts as an acid scavenging solvent. The term acid scavenger means collector of acids. An example in which the pyridine ring is used as an acid scavenger is the acylation of amine. Acylation of amine is a reversible reaction. A reversible reaction means that the concentration of the reactants and the concentration of product has reached a steady constant level at which they are at equilibrium with each other. For us, it only means that we get a low yield of our product, which is an alkyl or aryl acetamide depending upon the reactant that we use. To increase the yield of the product, what we need to do is to remove the byproduct. If we remove the byproduct, the reaction would propel forward as per the Lee-Chatterley's principle. This is where we use pyridine. When we use pyridine, the lone pair of electron on the nitrogen atom of the pyridine ring attracts and forms a bond with the hydrogen atom of HCl. Because the nitrogen atom lost its pair of electron to hydrogen, it develops a positive charge. It is this positive charge on the nitrogen atom which now attracts the Cl minus ion towards itself, forming an ionic bond and thus resulting in the formation of a salt, which is pyridinium hydrochloride. To sum up, what has happened here is that the pyridine has collected the acid or consumed the acid in its cells, leading to the elimination of the byproduct and propelling the reaction forward, thus increasing the yield of our product. Another example which proves that pyridine is an acid scavenger is the elimination reaction that is involved in the conversion of alcohol to alkenes. In this reaction too, pyridine collects acid and forms pyridinium hydrochloride. Although the pyridinium hydrochloride and the collection of this acid has no impact in the rate of the reaction or the yield of the product, but it is noteworthy that pyridine, the use of pyridine determines the stereochemistry of the product. It determines where the double bond would come. When we use pyridine, what we get as the major product is the anti-Zaitsev product or the lesser substituted alkene. This, however, is of no relevance to the current topic, what we need to note is the consumption of acid by the pyridine ring once again, thus positioning pyridine again as an acid scavenger. Use number 2, pyridine in denaturated ethanol. A denaturated ethanol is ethanol to which toxic additives have been added. Toxic additives are added to ethanol so as to make it unfit for consumption, so that the employees and workers working in an organization do not consume alcohol, and that the same alcohol can be used feasibly for industrial and laboratorial purposes. To speak in broad terms, different additives have different purposes to play in a denaturated ethanol. But to be specific on pyridine, pyridine is responsible for a nauseating odor in denaturated ethanol. The nauseating odor produced by pyridine acts as a repellent for consumption and signals the human brain that the consumption of such an alcohol would be lethal. Use number 3. Pyridine forms the main moiety and is used in the synthesis of the weedicide paraquat and diaquat. Both paraquat dichloride and diaquat dibromide are used in the control and management of weeds. Use number 4. Pyridine is used as an ingredient in mouthwashes. Cetyl pyridinium chloride, a molecule which has got pyridine as the main moiety, is used as ingredient in mouthwashes. This is used because it is known for its antiseptic property. Cetyl pyridinium chloride is known to prevent dental plaques and is used in the management of gingivitis. Gingivitis is the inflammation of gums. Use number 5, medicinal applications of pyridine. Pyridine is the main moiety and is used in the synthesis of a number of drugs. Videlicid, the isoniazid and ethionamide. The pyridine ring in both these medicinal compounds have been demarcated, and both of these drugs are known for its anti-tubercular activity. Omeprazole, pantoprazole and rabeprazole. All of these drugs contain pyridine as the main nucleus, which has been demarcated in the structures of these molecules. These drugs are proton pump inhibitors and therefore possess anti-ulcer activity. Sulfapyridine and sulfasalazine. Both sulfapyridine and sulfasalazine contains the pyridine ring, which has been demarcated in the drug molecule. Sulfapyridine is used for Durhing's disease or dermatitis herpetiformis. This is a condition that is developed in individuals who have gluten sensitivity. When such individuals consume gluten containing food, which is a common protein found in maize, wheat and barley, they develop red, patchy and itchy skin. This condition is called as dermatitis herpetiformis, and sulfapyridine is used in the management of such condition. While on the other hand, sulfasalazine produces a protective layer around the ulcer, giving it anti-ulcerative properties. Therefore, it is used in ulcerative conditions of the body such as ulcerative colitis, Crohn's disease and inflammatory bowel disease. Pyridostigmine. The nucleus of pyridine has been demarcated in the structure of pyridostigmine. Pyridostigmine is an anti-acetylcholinesterase inhibitor, making it an indirectly acting cholinergic agent. This makes it useful for weakness of the muscle in our body, a condition referred to as the myasthenia gravis. Dear students, I hope you have liked this video and have found it useful. If it was useful for you, please do not forget to share this video with your friends. Subscribing the channel would help you stay updated on various topics of chemistry. Thank you very much.